So, welcome to the second lesson of our module 4, where we are now going to look at what we call our line feeder protection. So, in lesson 1, we went into details about unit protection as a whole. And now here we want to see the means of doing this unit protection. So the first one we're looking at is what we call the pilot unit protection. And this is how transmission of information gets done between the equipment at our zone boundaries. We have a wire that is connected between the CTs that are sitting at each end of this line. And in that wire, we provide the path for that circulating current that is there under abnormal conditions and sensed by the relay so that the relay can be tripped. And this wire is thus used and it's known as what is a pilot wire. And we say that these wires or cables, as they are sometimes called, can be utilized for the control, for the protection, for the signaling, or for telecommunication and data transmission purposes. So in this lesson, we're really going to be looking at our unit protection on overhead lines as well as underground cables. And for this purpose, we then have these schemes, which we say can be more convenient if we have the relays at each end of that line or cable connected by this pilot wire or pilot cable that we're talking about. So our pilot relaying refers really to any relaying scheme employing a sort of communication between these relays that you have at each end. And it usually would then transmit a trip or a not to trip signal. And for this application, your relays have got both what we call an operating winding and a restraint or bias winding. So on our bias winding, really what it is there for, it provides a stability so that it stops the relay operating for what we call a through fault. And a through fault is a fault that is outside your zone of protection. If you will recall the faults that I put in on lesson 1 that were outside your zone of protection. So that we call a through fault. So this bias winding then makes sure that it only allows operation of the relay for when you have an internal fault. And we've got two basic arrangements that can be utilized for your pilot unit protection, and that is what we call a balanced voltage as well as your circulating current. So in this case, we're first going to start by looking at our balanced voltage scenario. And in the pictures in front of you, there is a left hand and a right hand picture. And it's really the same thing. One is showing it in a schematic diagram format, whereas the other one has done it as an equivalent circuit, showing it in a single phase manner. So what you have here is that you've got your CTs on either side of your line, and those CTs get connected to the relays at the bottom where you have that operating coil marked as O as well as that restraint or bias coil marked as R. So your pilot voltages are balancing each other if you have an external fault, all right? And you can see that I've put in that lightning mark on the diagram on the left hand side on top, which is outside the zone of protection. So for that one, nothing is going to happen because most of the current flows through what I call my bias coil rather than my operating coil. But if you now have a fault right in the middle where I now have a little arrow pointed on my top side here on the left hand diagram, if that is the case now, with the primary through current, your your secondary EMFs for our CTs were really opposed, okay? So therefore, we had no current in our interconnecting pilots. Whereas now, if I have this fault that is right in the middle of my zone, then I have got my circulating current condition in my CTs, and I will have then my relay coming into operation. Then the second scenario was our circulating current. And what you have here again, you've got the same scenario of having your CTs at the end of each of the lines. And if you had a through fault, which was outside this area of operation, then we would not have any imbalance caused within our CTs. So therefore, our relay really would not be in operation. So it would just go via the restraint or bias coil and go up to the other side. But the minute you had a fault that was within my zone, then you have a flux that will build up and will make a spill of my current, which will then result really into my current flowing into my CTs and into my relay, but on the operation side of my relay. So on this slide, we're continuing with the previous one for our current circulating. And on the left-hand side, really, it now shows us that single line diagram of what you had in the previous slide. And what has been picked up, that is a risk with this scenario on the left, is that this relay would also operate under transient conditions. Now, if you recall, transient conditions in chapter 1, we defined it as a temporary situation. It's not a real fault that has occurred on your system. So you do not want your relay to operate under transient conditions. And in order to avoid that, on our right-hand side, they've introduced at the bottom of that relay what we call a stabilizing resistance, and that stabilizing resistance will then get utilized in order to be a current setting reducer or a current limiting device so that your relay can be used as a voltage measuring device. So with the two arrangements of your balanced voltage and circulating currents, there are problems that could exist within your pilot wires, and they can be summarized as follows. Number one is if you had to have an open circuit scenario on your pilot cable, then your circuit could actually trip in the circulating current arrangement for a thorough fault, because it could easily say that that fault was within your zone, although it was outside. Why? Because already our pilot wire is open circuited and therefore cannot really differentiate between a fault within its zone and a fault outside its zone. Then the second scenario is if you had to had a short circuit onto our pilot cable. And if you had to had a short circuit, then the balance voltage arrangement could trip for that scenario. So to summarize these two, there is this table that's just come in now where I'm showing your protection type, your pilot cable open circuit, and your pilot cable short circuit. So under your protection type for circulating current, we're saying for your open circuit scenario, it could trip the circuit, whereas for your short circuit scenario, it's not operating. But then for your balance voltage on your open circuit scenario, we're saying it will not operate, but for your short circuit scenario, it would trip your circuit. So because of the problems that we have just picked up, we usually prefer to utilize your pilot wires for short lines. And short lines in transmission are defined as lines that are less than 50 kilometers in length. So if you had to have lines that are longer than this, then we need to have other means of doing this. You need protection communication. So the first one that we then look at outside now the 50-kilometer radius lines is what we call our digital current differential protection. So what we have in these scenarios is that from your CTs on your line, you've got digital relays at each end of the line that are going to be utilized. And these digital relays will really determine your values to represent the current that is flowing in that point of the line at any given time. And these are then communicated for comparison between the two relays at the opposite ends. Where the local and your remote digital values are the same, we say we have a healthy power line scenario. But where they differ, then this would indicate that there is a fault and that the circuit breaker at each end are to be tripped by a local relay that you have in your scenario. So your digital current differential protection really works on a time synchronization methodology. So, number one, for these digital relays, we need fiber optic because remember, we're no longer utilizing your pilot wires. Okay, so your fiber optic can go up to several kilometers without us having repeaters. I know of instances where you can go 150 to 200 kilometers without having repeaters, but then once you start having those long distances, then you would want to have a repeater station somewhere in the middle so that you can be sure that your signals are going even further and that their time is synchronized much properly. You have a phase comparison technique that gets utilized on a per phase basis, and your time synchronization of the measurements is then virtually important for this. So for that requirement, you need the transmission delay between the relays to be kept very small. And there's four methods in which this is possible. We have to assume a value, measurement during commissioning only that we need to know, and continuous online measurement we also need to know, and what is our GPS time signal. So under your assume a value, it is not used as the error between your assumed and actual values might be too great. So what we really use is your measurement during commissioning only, whereby we have provided reliable data of your direct communication between your relays. And as your signal propagation delays may change over your period of years. Okay, so remember that once you've commissioned and your equipment are on the plant for 10 to 15 years, everything else changes around you. So obviously that commissioning value you had is not going to be so good as it was when you first started out your system. So for this type of scenario, that's why then you need to repeat your measurements as your years continue while you are utilizing this service or this equipment. The technique is less suitable if rented fiber optic pilots are utilized. So if you're the owner of your fiber optic, then this is the much better use for you to utilize. Okay, I'm going to summarize the continuous online measurement, all right, for you to be able to understand what is really happening. So you've got your two relays, A and B, at either side of this line. And now what happens is that relay A will be the first one that measures something on the line or on your network, and it will take that information and send it to relay B. So at the time that it takes that information, we can call it typically a TA1, okay? Then it sends that information, the time that I've measured this information plus the information gets sent to relay B. So when it gets to relay B, it doesn't get there at that time, which was TA1, okay? there will be a propagation time, which is the time it took from relay A to go to relay B. So relay B will measure saying I received information from relay A at the time relay A sent it plus my propagation time. Then I went and I measured what is out on the field. And then I take that, I compare the two scenarios, and then I send the information back to relay A. So again, relay A does not get it at the time that relay B has sent the information. So there's various times. That's why I'm saying I'm not even going to go into there, but I want you to understand that when these comparisons are being done by the two relays on either side of that line, the time differences, we need to take account for them so that we know exactly when your fault actually occurred as an engineer that needs to go and do an investigation later on. So that's why the relays, they keep on playing with the time differences between them, that I picked up this time and then I sent you information to be at that time, and I picked up this information at this time and then I sent you the information at that time, so that when now later on, when you do your research as an engineer, you can be able to pick up the relay A and pick up the relay B information. And when you correlate the two, you can know exactly more or less at what time did your fault actually occur on your system. Then we've got the GPS time signal, right? So for our GPS time signal, we say this is a robust technique that we have. And this robust technique really involves both of your relays, your relay A and your relay B, being able to receive your time signal from your GPS clock source. So they receive that time from your GPS, and the propagation delay on each communication channel is no longer required to be known or calculated, as both relays are synchronized to a common time signal. So relay A does no longer have to record what time I sent you the information, and neither does relay B, because they're getting both the times from the GPS. So your GPS does that for them. So that GPS signal must be capable of reliable receipt under all atmospheric conditions. We can't have your GPS signal not being able to record because the weather was bad, there was wind, there was rain, there was snow. It needs to be a really reliable source as it takes out that continuous online measurement of time. So also under our line feeder protection, we have something that is called a mesh corner and or a 1.5 breaker switched substation. Is really the same thing. So in the single line diagram that you have, you can see that on the top part I have a bus bar, then I have a circuit breaker, and then I had a circuit one that was going out. Then I had another circuit breaker and I had a circuit two that was going out, then another circuit breaker, then I went back to another bus bar. So this is why we're saying we have a 1.5 breakers, because if you look at it, it was a breaker, a circuit, and another breaker. Then that breaker was shared to your circuit two, and then there was another breaker. So you had one breaker dedicated to each circuit one and circuit two, and then the one breaker in the middle is half because it is shared between your circuit one and your circuit two. This method is expensive and is used for important high voltage circuits only, and the problem exists in protecting your feeders due to the location of where your line CTs might be, as either your bus 1 or bus 2 or both can supply your feeders at any time. So your CTs need to be strategically placed. Two alternatives are used to overcome the problem that we have here. So the first way that we can be able to overcome this, if you look at the diagram on where you have feeder A coming out, so you've got your CTs on either side of your feeder A, and what they've done is that they've connected the two CTs, and then they have a connection from that connection of the two CTs going into your relay. Then on your second alternative, is instead of connecting the CTs to one another, they take both CTs and they connect them as inputs into my relay. So my relay, instead of having one input coming in, it will have two that are coming in. So in the case of a terafort, as shown, the relay connected to feeder A theoretically sees no unbalanced current, and hence it can be seen as stable. However, with the line disconnect switch open, no bias is produced in the relay, so your CTs needs to be well matched and equally loaded if mal-operation is to be avoided. If you now look at your feeder B, the relay theoretically sees no differential current as well, but it will see a large bias current when the line disconnect switch is open. Okay? And this provides a high degree of stability in the event of transient asymmetric CT saturation scenarios. So therefore, the technique of feeder B is what would be preferred. Sensing of the state of the line isolator through auxiliary contacts enable your current values transmitted to and received from your remote relays to be set to 0 when the isolator is actually in an open position. So hence your stub bus protection for the energized part of your bus is then possible with any fault resulting in tripping of your relevant circuit breaker. Then we have got carrier unit protection schemes that can also be utilized on our line feeders. And these are carriers generally insensitive to induced power system currents, since your systems are designed to operate at much higher frequencies. But each medium may be subjected to some noise at the carrier frequencies that may interfere with your correct operations. So here again, you can have a current differential scheme which is used to convey both the phase and magnitude of your current on either end, or you can have a phase comparison protection scheme of which your communication between your relays commonly uses what we know as a PLCC or a frequency modulated carrier modem technique. And the diagram on the right hand side really shows how this scenario is put together. As we then complete lesson 2, we complete it with the example that is shown in the prescribed textbook, where you have a line. It's really a small line because it's a 25-kilometer line, but they've decided to utilize digital communications link, of which you could have also utilized your pilot because it's less than 50 kilometers. So they give you an impedance of your line and they give you the shunt charging current of your line. And they tell you that this is the type of differential relay that is being utilized. And so for that relay, your bias current threshold setting is equal to 2 per unit. Your lower percentage bias setting is 30%, and your higher percentage bias setting is really 150%. And for you to be able to do anything on this, you can go to your current charging and you take that and multiply it by the 25 kilometers, you will get the 1.625 amps. And if you took that for this type of a scenario, it would usually be your IS1 must be at about 2.5% times the steady state current charging. So you take that 1.6, you multiply it by that 2.5, you will have 4.1 amps. And if you take that ratio of your CTs of 400 which is to 1, that means you take that 4.1 amps that you just got, you divide it by the 400 so that you can change it into a per unit value. It would give you 0.01 per unit. So that would be really your IS1 current setting. So because then you have your nearest available setting on your IS2 is sitting at 0.2 per unit, This will then give you the points of the relay characteristic that you need to be able to put in.